Light Chapter Part 3. Hello everyone, hope you are doing good. So now today I'm just going to continue the leftover small fraction parts from the light topic. Actually, we completed a part 1 and part 2 related to a light topic. If you people didn't watch the part 1 and part 2 video, you can just go to YouTube, type tuition, a YouTube channel, but it's not a tuition actually. You have to type 2XION. Literally, you have to type like that. It's pronounced as tuition, an official YouTube channel where you can see my videos related to 10 science, your light chapter, part 1 and 2. That is related to your reflection, refraction, all the laws and all. Because once when you see this video immediately, you may not understand what is currently going on. So for that, you can see the part 1 and part 2 video. Then when you come back to this third video, you will know where you are. Right? Okay. Let's start the leftover topics from our light. So before that, I'll just summarize what we saw in the last class actually. So we saw the refraction of light. That is, what is the refraction of light is the phenomena of bending of light when it travels from one medium to the another. That is from your air, suddenly when it's traveling into the water, right? So it may not have the same speed literally, right? So it will have a different mode of speed, right? So that is your refraction. And we saw the law of refraction of light, the incident ray, the normal ray, the refracted ray, all lie in the same plane. We saw all those things. And we saw this famous sin I by sin r is equal to constant. Right? Hope you all remember this. And then we saw the spherical lenses. That is your two kinds of lenses, your convex lens and your concave lens. Alright. So we saw all these things in your last part. And then we saw what is your principal focus, principal axis and focus. Do you people remember all these terms actually? So in your mirror, you don't have optical focus actually, but in your lens, there is a new parameter comes, that is your optical focus. So what is your optical focus is nothing but the center point of your lens. See, can you see the center point of your lens? Got it? So next we are moving into the rules for drawing ray diagram. This is as simple as your mirror. What are the three rules you saw in the mirror? Do you remember? The same rules is only followed here actually. But the third rule alone get different here. Okay. So we'll just see that. So whenever a ray of light, this is your principal axis. Can you see this is your principal axis? So whenever a ray of light just passes parallel to the principal axis, it will just pass to the focus after refraction. So that will be your rule number 1. So whenever a ray parallel to your principal axis passes through the focus after refraction. What will be your rule 2? Whenever a light passing through focus, what will happen? You'll get a ray which is parallel to your principal axis, that is after refraction. These 2 points are same in your mirror too. But what is the third point here? It is a ray of light passing through the optical center goes straight without changing its path. So whenever a light passing through the optical center, it will go straight without any change in its path. But what we saw there, you remember what we saw there? When a light passes through your center of curvature, it retraces its own path again. It comes back to the own path again. That is the difference in your mirror and your lens. Okay, that's it. So keeping this rule in our mind, we are going to see the next thing. That is your rules for drawing a ray diagram. That is whatever I have explained before, right? Okay, so whatever I have explained before, we are just going to see in a diagrammatic manner. Okay, we already saw this. You're used to this, right? So what will be your, this is your rule 1. So if you can see, this is your convex lens. Okay, so see, a ray of light parallel to the principal axis. Can you see? This is your ray of light. Can you see? So a ray of light parallel to your principal axis, that is, it passes after refraction. So once when it passes through the lens, it undergoes refraction, right? So after refraction, what happens? It just passes through your focus. It just passes through your focus. And you know what is this actually? This is actually your principal axis. This is your optical center. Optical center. And this is your first rule, right? It's as simple, right? What will be your rule 2 actually? A ray of light passing to the focus. So, whenever a ray of light, when it is passing to the focus, you will get, after refraction, you will get a ray which is parallel to your principal axis. Can you see? Parallel to your principal axis. That will be your rule number 2. Okay. So, what will be your rule number 3? So, whenever a ray of light passing to your optical center, so this will be your optical center as I mentioned before. So whenever a ray passing to the optical center, it just goes straight without any change in its path. Got it? So the 3 rules I told you in a statement, and this is your ray diagram. So keeping this ray diagram only, we are going to learn the different positions of the image and the object for your convex lens. Okay. Can you see here? So here the formation of image by convex lens for different positions of object. For different position of object. So when you can see over here, they have tabulated the position of the object, the position of the image, the size of the image and the nature of the image, and here comes your ray diagram. If you can see from here, the object is somewhere at the infinity actually. Can you see? The object is somewhere at the infinity. See. So the position of the object is infinity. So that they didn't mention where the object is actually. It is somewhere at infinity. So whenever a ray of light from infinity, can you see a ray diagram? Infinity, what will happen? It's the same phenomena. Whenever a ray parallel to your principal axis, after refraction, it just passes through your focus. Can you see? All are passing through the focus. And whenever a ray which is passing straight to your optical center, it doesn't even change its path. Okay, but here only one rule is followed here. So whenever a ray passes through your, that is whenever a ray passes through your lens, which is parallel to your principal axis, after refraction, it passes through your focus. Okay, this is possible only when the object is at where? Infinity. And where you get the position of the image, the position of the image is found at F2. Here only your position of the image is found. Got it. Since I don't mention the object, they're not mentioning the image. They are just mentioning F2. That's it. So that there you can see the position of the image. And what about the size of the image? Since we don't know where is the object at all, it is at infinity. Okay, so how can we guess the your shape of the image, right? So it is extremely diminished. It is extremely diminished. And what will be your nature? It's real and inverted. It is real and it is inverted. And next thing, next where you're keeping your position of the object is, you're just keeping over here. Can you see your AB here? Where is your object actually? It is behind your, and your focus it will go on like F1 to F1. It will go on the category of your double. That is your 2Fn, then 4Fn, then 6Fn. It will keep on going. Okay. So now, behind 2F1. Can you see? This is kept behind this 2f1. Here your object is placed and the same formula, the same rules only. So can you see, when a ray of light which is parallel to your principal axis, once when it passes through your lens, after refraction it passes through your focus. Got it? And when a ray which is passing through your, this is your second ray, right? When a ray passing to the optical center, it doesn't even suffer from its the original path, and it directly go and meet it over here. Okay, so where you can see the images, your image can be seen between your focus f2 and 2f2. Here only you can see your image. Here also, what will be your size of the images? It is diminished and it is real and inverted. Got it? So the first case is common for your mirror. But the second case is you are placing the object where behind the focus 2f1 and it is in front of the mirror. Okay, the same phenomena when a ray parallel to your principal axis, okay, once after the refraction it passes to the focus, and a ray which passes the optical center, it doesn't even like divert from its original path, and they meet at the point between your f2 and 2f2. Got it? So this is in the case when you keep behind 2f1 at a finite distance. So first you have kept at infinity. Now you have kept at a infinite. Like before you were kept to the infinity. Like infinity. You just don't know where the object is. But now you are just kept in a finite distance. But that too behind your 2f1. That is, this is in the case 2. And what will be your case 3 years? You are keeping the object exactly at 2f1. You are keeping the object exactly at 2f1. So can you see? See, yeah, 2f1. And the object is placed exactly at 2f1. Can you see? The object is exactly placed at 2f1. Okay, so the same rules are followed here. So what will happen here? A ray, when it's parallel to your principal axis, when it passes through your lens after refraction, it just passes through your focus. There you'll get the image. Okay, the same thing when a ray which passes through your optical center, it doesn't even it doesn't even change its original thing. So it will meet again there. So you'll get the image exactly at 2f2. You'll get the image A prime B prime exactly at 2f2. So when you keep in your mirror, when you keep at the center of curvature the object, where will be your image? It will be same in the center of curvature. Do you remember? So the same thing, when you keep an object at 2f1, you'll get the image back at 2f2. And can you guess what will be the size of the image? It will be same size. It will be same size, and the nature will be a real and inverted. And the nature will be real and inverted. So far, well and good. Hope you understood. Okay, the first three different position of the object and different position of the image, right? Okay, so now we are moving to placing the object between f1 and 2f1. Can you see? This is your f1 and this is your 2f1. This is your f1. Where is your object is placed? The object is placed between your f1 and 2f1. Can you see? Here also the same rules is only repeatedly followed here. You need to remember only where the position of the image is. Fine. So here the same thing, when a ray of light which is passing through the lens after refraction, it just passes through your focus. Okay, there you'll get the image here. And the same thing when a ray of light which passes through the optical center doesn't even undergo change in its original path, you'll again get the image intersection here. So here you'll get the image A prime, B prime, and where you'll get the image actually, you are getting the image behind your 2f2. This is your 2f2, right? But where you are getting your image, it is behind your 2f2. Okay. So here your size of your image is changed from diminished to magnified. It is slowly getting into your eyesight, I can tell. Okay, so it is magnified. Okay, but even though it is magnified, it is still real and inverted. It is still real and inverted. Got it? It's still real and inverted. And what will be your at F1 actually? At F1, actually you cannot see this two-ray diagram. I'll just switching off my sorry for the trouble, people. So in last slide, you cannot see your fifth and sixth position. So I separately tabulated over here. Can you see here? The fifth position will be your position of object at focus F1. Can you see at focus F1? So you're keeping your object, where you're keeping your object actually, you're keeping your object over here. F1 is over here. So the same phenomena. So what is happening? A ray which is passing parallel to your principal axis after refraction, which just passed through your focus, and a ray which is passing directly into your optical center will just pass without any deviation. Okay. So here, where will be your position of an images? It will be somewhere at infinity. So whenever you keep an object at focus F1 that is little bit closer to your lens, what is happening is that your image is somewhere far infinity. Okay. So here what will be your relative size of the image will be, it will be highly enlarged. It will be highly enlarged and still your nature of image is real and inverted. Still the exact position we didn't deduct it. Okay, still your nature of image is real and inverted. So this is your fifth position. So in your fifth position, what is happening? You're keeping the object at F1 and you're getting your image somewhere at infinity. That will be your fifth position. Okay. So what will be your sixth position is that it is placed between F1 and optical center. So you are keeping the object between somewhere. See, this is your optical center and this will be your focus F1 and this will be your optical center. Your object is placed between your optical center and focus F1. So the same thing. Okay. So what is happening? A ray parallel to your principal axis passes through your focus, and a ray which is passing to the optical center without any deviation, it is going in its original path. So here what is this dotted line symbolizes? Here what is this dotted line symbolizes is that symbolizes the position of the image actually. You're getting the image where? You're getting the image where? On the same side of the lens as the object. On the same side. Your lens is also in the same side. And the image is also in the same side. So the portion of the image you are getting in the same side of the lens as the object. So you are getting the position of the image on the same side of the lens as the object. Right. So here what will be your relative size of the image? Your relative size of the image is enlarged. It is enlarged. What is your nature of the image? It is virtual and erect. It is virtual and erect. Nature of the image will be virtual and erect. Okay. So these are the 6 cases you have seen in your convex lens. These are the 6 cases you have seen in your convex lens, which will be the opposite of your mirror. In mirror, you would have seen the 6 cases in concave and 2 cases only in convex. But what has happened here? So far, you have seen 6 cases in convex lens, and now we are going to move to your 2 cases in your concave. And before going into that, we'll have just like in the last thing, we just tabulated your full thing of your concave mirror, right? So the same thing only. The image formed here by a convex lens. Okay. So what is actually your position of the object? We are just tabulated here. So that is where you'll keep the position of the object actually between F and lens. Okay, so the position of the image you got on the same side as the object, right? Same side as the object. So what will be your size of the image actually? Your size of the image will be enlarged, and your sixth case is first one. Okay, don't get confused. Your sixth case is the first one. Nature of the image will be virtual and erect. Nature of the image will be virtual and erect. The last case we saw, right? The same case only it's tabulated here. So that is in between F and lens. Okay, so on the same side as the object. Next, at focus. At focus, if you're keeping the object, you'll get the image somewhere at infinity. You'll get the image somewhere at infinity. And your size of the image will be highly enlarged. Your size of the image will be highly enlarged. And the nature of the image will be a real and important. So what about your nature of the image? Your nature of the image will be a real and important. And when you keep in between F and 2F, F and 2F, that is prime, that is this side. Okay, so you can also call like F1 and 2F1. So when you place between F prime and 2F prime, you'll get the portion of the image behind 2F. You'll get the portion of the image behind 2F. And what will be your size of the image? Your size of the image will be enlarged. So your real and important. So you can study it will study like this. So it will be easily you can take the things inside if it is tabulated like this. So if you if you're preparing for an exam, you can just keep this tabulation and the ray diagram. So you can just look the tabulation, vice versa, you can just draw the ray diagram. So it will be very useful for you. And this will be your fourth position, that is your 2F1 or 2F prime. The position of the image you can find at 2F. And what will be your size of the image? It is same as the object. So when you keep the object at 2F, you will get the images also at 2F, right? We have saw in the ray diagram. So here in this case is also real and inverted. What about your your fifth case is nothing but behind 2F1. If you're keeping the position of the object is behind 2F1, you'll get the position of the image between F and 2F. The position of the image is between F and 2F. So it is highly diminished. It is highly diminished. Here also we are going to get real and inverted. Real and inverted. And at infinity. And at infinity, if you are keeping the object, you'll get the image at the focus and it is highly diminished. Here it is also real and inverted. Here it is also real and inverted. So we saw the image formed by convex lens both in your ray diagram format and your tabulation. So next we are moving into the image formed by your convex lens. Okay. So this since it has only two things, the tabulation is also there and the ray diagram is also there. Okay. So now position of the object. So the position of the object is when you keep at infinity. Okay, when you keep at infinity, this is your first ray diagram. So when you are keeping at infinity, you just don't know. Okay, so where will be your position of the image? Your position of the image will be at focus F1. But what is this dotted lines will denote? It appears. It just act to meet. Okay, so that only this dotted lines. Okay, so what will be your size of the image? Your size of the image will be highly diminished and point sized. And the nature of the image will be virtual and erect. Your nature of the image will be virtual and erect. What will be your second case actually? So when you place the object between your optical center and between the infinity and the optical center. Okay, can you see? So this will be your this will be your optical center. In between your optical center and your infinity somewhere. So here they have kept. See, here they have kept AB. Okay. So what will happen is that you will get the position of the image between F1. Here the position of the images. Can you see? The position of the image between your optical center. The position of the image will be between optical center and focus F1. Right. So what will be your size of the image? Your size of the image is diminished here. And the nature of the image will be virtual and erect. So what will be your second portion is that when you keep the object between the optical center, okay, and the optical center of the lens, between infinity and the optical center, you choose a point exactly. So this is your optical center, this is your infinity. So where you are keeping is in between here, in between here. So when you keep over here, this is your optical center and somewhere infinity, I don't know. So I've kept in between here. So where you'll get the image? I'll get the image in between your focus F1 and the optical center. Your focus F1 and the optical center. So this is nothing but image formed by concave lens. There are only two things. One, when you keep the object at infinity, you'll get the image at focus. It's same as your one first ray diagram in your convex lens, but here they just act to meet. Okay, so the size of the image will be highly diminished point size. Nature of the image will be virtual and erect. What will be the second case is you can choose the position of the object somewhere between the optical center of the lens and infinity. So when you choose the position somewhere between the optical center and infinity, you'll get the position of the image in between your focus F1 and the optical center. In between your focus F1 and optical center. Okay. What will be the next thing is your sign convention for lens. The same thing we saw for your mirror, right? So the same thing only we are going to follow for the sign convention for lenses too. So the sign convention for lenses are same as those for spherical mirrors, except all the distance are measured from optical center. So here you have a optical center. So it is mandatory, or I can tell it is compulsory to measure the distance from the optical center. Okay, so from the optical center only, we'll just allot the particular sign convection for the lenses. So the distance to the right of the origin will be positive. Positive x-axis is considered to be positive. Right side of the origin. Can you imagine the graph? What will be the right side of the origin? It will be positive, right? Okay. So while that to a left side will be negative. Left side will be negative and your right side will be positive. So the same thing. So the positive while that to its left is negative. So the distance above the principal axis, this is your principal axis. So whatever you are visualizing above principal axis, that will be taken as positive. That will be taken as positive. But what, see, positive. While those below it, which will be taken as a negative. So below it, okay. So those which is taken below are just taken as negative. Or just taken as negative. So those which is below is taken as negative. It's simple. Right side positive, left side negative. Top side positive and bottom side will be negative. That's it. Okay. Next is your lens formula and magnification, as we saw the lens formula for concave convex mirror 2. So the same thing, we need not go for the derivation right now for your standards. Okay, so for a 10th grade, so it is okay if you learn just the formula. Once when you are moving into a high level, you can learn how we got this formula, maybe derivation. So lens formula. So what is your lens formula is nothing but 1 by V minus 1 by U is equal to 1 by F. We already saw in your mirror. So you know what is your V? What is your V? Image distance. What is your U? Object distance. And F, you know, it is your focal length. Right. So now magnification, you also know your magnification. So what is your magnification? Is nothing but height of the image by height of the object. So height of the image by height of the object. That is your h prime by h. Height of the image by height of the object. H prime by h. So I can also denote it as m is equal to h prime by h. That is equal to v by u. Actually, it's an image, right? So I can write v. This is your object, so I can write u. So where u is the object distance and v is your image distance. V is your image distance. Next is your power of lens. So we have like they have allotted a unit to power of lens. There is a unit for lens. The power of lens is the reciprocal of its focal length actually. So it's a formula over here. So when the power increases, you may know that your focal length will decrease. When the power increase, your focal length will decrease. When the focal length increase, the power will decrease, vice versa. So the SI unit of power of lens is called diopter. So this is only the SI unit of your power of lens. So it is called diopter. It is denoted by the letter capital D. It is denoted by the letter capital D. Here we're going to discuss few answer problems inside book. That is the example problems. Right. So we'll just discuss few problems and then the summarization in your next lecture. Thank you guys. Bye.